So good evening. We will start this session in just 2 minutes. We'll wait for other participants to join the session.
कोई नहीं, इतना होता है, इतना बच्चे को नहीं सोचना चाहिए.
So good evening. Good evening, everyone. You all are welcome to the problem solving session number 3 for the course Biointerface Engineering. This is the discussion for week 3 course content, as well as we'll solve some of the questions related to it. So let's move ahead. So the course is Biointerface Engineering. The course instructor is Dr. Lalit Mohan Pandey. He is the Associate Professor of Department of the Biosciences and Bioengineering, IIT Guwahati. I myself am Shilpa Nandi. I am a PMRF in the Center for the Environment, IIT Guwahati. So this is a doubts and interaction session which runs every week, that is every Tuesday from 7 to 9 p.m. If you have any queries, you can raise your hand, unmute yourself, and then raise a query, or even the questions can be posted in the chat box. Other than that, you can always post your questions in the discussion forum in the Swayam portal so that we can address all your queries there. So all these questions will either be addressed in the forum or in the next week's live session. Okay.
Ma'am, can you send the previous question and book, any book, can you send in the mail?
Okay. Okay, we'll
Last
discuss.
time you will said that ki I will send in, I will share the link in mail and in previous question also.
Yes, the questions are already available in the Swayam portal. If you are not uh, known to that, did you go to the portal and you can check there in the last tab? It's already given the problem solving assessment. All the PPTs as well as the videos are available there.
Okay, ma'am.
Yes, I'll show you. Just right now, if you want, I'll show you. Um, just wait a minute. I'll open that page so that it will be easier for to understand from where to access that. Just wait a minute. I'll show you from where you can go and Just get all the PPTs as well as the video links. It's stored in a drive which you can get the link to. So just wait a minute. So you can look at this. You can just access your access this portal using your mail ID or whatever you have registered through, right? So can you see, Sonali?
Yes, ma'am.
Yes. So in the left hand side, when you see there is a course outline, there is week 0, week 1, week 2. Then at the end of the tab, at the end of the panel, you can see there is an
Problem
option
solving
for,
session.
yes, yes, right.
Yeah.
So just there you can click on it and go to the first option, that is the problem solving session. And when you click on it, it will redirect you to a link from where you can just see there is a click here option, and you have to just click on it. You will be redirected to a Excel sheet. Can you look at?
Yes,
Yes,
ma'am.
ma'am. Just wait, I'll show you the Excel sheet also. So after just clicking on this click here option,
Yes.
yes, just wait a minute. Yes. So this is the Excel sheet you will be redirected to. As you can see here, week 1 content is given, then week 2 YouTube link is also given. Then in the next tab it's given presentation folder link. You can click on that and you can access all the PowerPoint presentations. Right?
Okay. Yeah. Okay, ma'am.
Okay. If any other problem is there, you can tell me. And um, for the book, did you just search it in Google? You know the name of the book, right?
Intermolecular forces.
Yes. For the book also, it's given in the portal as well. I'll show you once. However, okay, in the end of the lecture, we shall discuss about it. If you're not able to get the book, just give me your mail ID, then I'll share you the book.
Okay, ma'am.
Okay,
Okay.
fine. So let's move ahead. I'll just start presenting. Yeah. So this week's outline of the live session is we will discuss about the week 3 course content. That is lecture number 7, lecture number 8, lecture number 9, which were the methods for surface tension measurement. Next is methods for contact angle measurement, and lastly the determination of surface tension of solids. And at the lately we'll solve about the week 3 related assignment questions and answer discussion. So these questions are not specifically, they won't come in the exam or may also come in the exam, but this will ultimately help you to solve the assignment number 3, that is assignment week 3 assignments, as well as the future questions. Fine.
Yes, ma'am.
Yes. So let's move on and discuss about the week 3 course content. I hope that you all have went at least a bit recap about the week 3 content. However, we'll go through it. So the lecture 7, it was about the methods for surface tension measurement. Basically, what are the various methods by which you can measure the surface tension of any liquid, right? So there are actually three different types of categories. That is, one is detachment based method. Second is determining the shape of the static drops, and third is dynamic methods. So in the first case, detachment based methods, we have drop weight method, ring method, and Wilhelmine slide method. In On the basis of the shape of the drop, we have three methods, that is pendant drop method, sessile drop method, and third is rotating drop method. Lastly, we have dynamic methods, which involves like flow method, capillary waves, maximum bubble pressure method. Okay, so moving on to drop weight method, that is a detachment based method. What happens? A drop moves through a capillary, and this drop, while falling, around 40% of the drop volume is left, and the tip of the tube give around W dash lower than the actual W. So W is the weight. So this can be determined using the Tate's law, that is W is equal to 2 pi r gamma f. R is the radius of the drop, gamma is the surface tension, and f is the correction factor. So why do we need this correction factor? Uh, This correction factor is actually needed because it's already written here that during the falling of the drop, around 40% of the drop volume is left at the tip of the tube, giving W dash. So W dash is given as 2 pi r gamma f. And this f is actually directly proportional to r by a, which is directly proportional to r by v to the power 1 by 3. Now gamma can also be determined by mg divided by 2 pi rf. So,
Ma'am, I think your slide is yeah, now this is okay. Yeah.
oh, wasn't it visible? Um, so is it visible now?
Now visible.
Okay. If you are not able to look at the slides, I think you should show, but uh, just wait a minute. I'll stop the presentation and I'll try once again. Yes. Just tell me if I'm changing the slide, whether it is visible or not. Okay.
Okay, ma'am.
Okay. So I just went to the next slide.
It's visible.
Okay. Fine. Okay. So the drop, apart from drop weight method, we have this ring method. So a ring made up of platinum usually is dipped in a liquid. It can be either a single liquid or a liquid 1 and liquid 2. So in this case, we have this formula, that is W total is equal to W ring plus 4 pi R gamma. Again, here we use this correction factor F, which corresponds to gamma by V is equal to F bracket R cube by V or R by R. Next is this Wilhelmine slide method. So in this case, we don't use any ring, rather than we use a slide that is made up of again platinum or glass. So this slide method also is similar to the ring method. Just the difference is, in that case we use rings and this case we use slide. So the W total here is given as W plate plus gamma P. So gamma P is given as 2L cos theta gamma. Next we have the shape based determination of surface tension, that is pendant drop method. In this case, the shape of the drop determines the surface tension. So the pendant drop method is based on Young's Laplace equation, which is delta P, P internal minus P external which is given as gamma 1 by R1 plus 1 by R2. Now 1 by R1 and 1 by R2, as you can see in the figure, R1 is the peripheral axis radius and R2 is the arc axis radius. Next is sessile drop method. So a drop placed in a rough surface can be given by the surface tension can be measured as del rho g h square by 2. So the density, gravitational constant, and h square. H is the height of the drop. Next is rotating drop method. This is also a shape based method for surface tension measurement. So a liquid drop having a liquid which is a liquid-liquid interface. This will have two phases basically, phase 1 and phase 2. So in this case, as you can see, it is written the density for phase B will be greater than the density for phase A. Now when you rotate this, what will happen? The phase A will elongate, and as it elongates, it changes the shape from circle into an ellipsoid and then into a cylinder. So basically there are two phases. One is phase A and another is phase B, and it is basically a rotating drop method, as you can see from the heading itself. So the whole phase 1 and phase B is inside a capillary basically. So this capillary, when you give us rotate it at a certain RPM, what happens, the phase A will elongate within the phase B from a circle to ellipsoid and then to a cylinder. So the surface tension here can be measured, surface, as you can say, the interfacial tension, that is liquid-liquid interfacial tension, can be measured by, this is the angular velocity squared del rho r cube by 4. So this is basically Vonnegut equation. This was given by Vonnegut. Okay, moving on, we have flow-based method. Flow-based or dynamic methods. These consist of flow methods, capillary wave method, and third is maximum bubble pressure method. So in case of flow method, there is a non-circular orifice, and this with a certain speed, they have an elliptical, which is actually an elliptical jet, and the drop changes its shape from circle to an ellipsoid and then again to a circle, then to a vertical ellipsoid, and so on. So this was given by Rayleigh and Bohr, wherein they mathematically proposed that gamma can be given as 4 rho v square 1 plus 37 b square by 24 r square divided by 6 r lambda square in the bracket 1 plus 5 pi square r square divided by 3 lambda square. So next is capillary waves method. In this, the wavelength of the ripples on the surface of a liquid determines the surface tension. So this wavelength, Kelvin here mathematically proposed that V square is equal to G lambda by 2 pi plus 2 pi gamma by rho lambda. So gamma can be interpolated from the first equation as rho gamma rho lambda cube divided by 2 pi tau square minus G lambda square rho by 4 pi square. Lastly, we have maximum bubble pressure method. So in this case also, we measure the liquid surface tension. So it involves the increasing the system volume relative, which is basically proportional to that of the bubble. So we can track the bubble formation frequency using an electric and acoustic sensors, and basically this technique is applicable to the study of only the surfactants and polymer adsorption from the solution. Fine. So till now we have basically discussed all the methods which are used for surface tension measurement in case of liquids. Next, we'll move on. Before moving on to the lecture 8, that is methods for contact angle, we may also discuss about the solid liquid interface, That is the Young's equation and Young-Dupré equation, which was also discussed in the last week's content. However, we will repeat it again. Right. So, talking about the solid-liquid interface, a solid and the interface between a solid and a liquid drop is basically a solid-liquid interface, and the angle made between these two is the theta, that is the contact angle. So, according to Young's equation, gamma LV, that is the surface tension of liquid with respect to the vapor. V is vapor, L is liquid, and V is vapor. Cos theta, theta is the contact angle, can be given as gamma SV, that is the surface tension of the solid, minus gamma SL, that is the interfacial tension between the surface and that is the solid and the liquid. Right? So cos theta can be written as gamma SV minus gamma SL divided by gamma LV. Similarly, spreading coefficient was can be given as S is equal to WSL minus WLL. So WSL can be again written as gamma SV minus gamma LV minus gamma SL. So altogether S can be calculated as gamma SV minus gamma LV plus gamma SL. So if S is greater than 0, spreading of the liquid occurs spontaneously on the surface, which is also known as the total wetting. And if S is less than 0, there will be no spreading but forms a spherical cap at the equilibrium. So this is termed as partial wetting. Fine. So we will move on to the methods for contact angle measurement. Till now we discussed about the methods for surface tension measurements in case of liquids. Now we will see what are the methods for contact angle measurement. So contact angle measurement, again we have certain methods. First is sessile drop method, which is the drop when placed in a surface, any solid surface, you can measure it using a goniometer. So this instrument, goniometer, as you can see from the figure, resembles quite closely to a horizontal microscope. If you have ever seen a microscope, it is a vertical microscope, a vertical, and this is horizontal in nature. So what we have is here, there is a light source, then there is a diffuser, and after that we have a dispersing system, that is a syringe, and below that there is a drop. So when you push the syringe, the drop will just fall over the sample, that is a solid sample. That solid sample can be anything, whatever you're testing. It may be glass, it may be any other source such as any rock, and just in front of it we have a camera. So this camera is able to capture the image of the drop that falls in the surface of the solid. So again, this is connected to a data acquisition system, that is a computer which is already equipped with certain softwares. So this particular method was been given by Zisman and co-workers. So Zisman and co-workers employed a microscope objective to view the angle. So basically what we are seeing, the contact angle between the drop and the surface. Fine. So this is as you can see from the heading itself, sessile drop method. So the drop is not moving, right? So next we have another method, that is drop shape analysis. Again, this is a part of sessile drop method itself. So in case of drop shape analysis, there is a tangent method and another is height weight method. So if I consider the drop placed in the surface as a round, as a sphere, if I connect the dots of the other part of the drop, taking it as an imaginary circle, what you can do is you can place a tangent and then you can determine the contact angle. And as you can see in the second figure, that is under the height width method, basically the height of the drop divided by the width of the drop can be written as tan theta, that is tan theta is equal to h by r, right? So tan theta is h by r, and again if you are measuring the contact angle specifically, So this will be 2 theta, because theta is giving only the half of the angle. It is not able to give the whole of the contact angle. So this theta can be multiplied by 2 to get the contact angle, right? Again, for contact angle measurement, similar to that of surface tension measurement, we have a Wilhelmi slide method wherein you can determine the contact angle as well. So in this case, W total is equal to W plate plus gamma cos theta P. So P is the perimeter of the plate. So gamma cos theta can be written as the del W by P. So uh, in this case, sin theta can be written as 1 minus rho gh square by 2, uh, sorry, 2 gamma is equal to 1 minus h by a to the whole square. So when we are going to solve the question, you will understand all these methods in a better way. At least today I have included certain questions which will help you think about how you can just measure this contact angle as well. So there's nothing to worry. We'll also solve some numericals so that you can get an idea about it. So we'll move on to the next. So lastly, we all till now we determined the contact angle for liquid, but there is also a method for contact angle of a finely divided powder. So how you can determine the contact angle of a finely divided powder? So powder is compressed into porous plug so that the capillary pressure required to pass a non-wetting can be measured. So this porous plug is regarded as a bundle of capillaries of average radius r, and hence for wetting liquid this del P0 can be given as 2 gamma dash LV by R, and for non-wetting liquid it can be given as del P 2 gamma LV cos theta by R. So if you see, if you like divide these two equations, you can get the cos theta. So R will be eliminated, R will cancel out, and what we are left with is cos theta can be given as del P gamma dash LV by cos P naught gamma LV. Right. So we can also determine the contact angle of a finely divided powder. Moving on, lastly, we have determination of surface tension of solids. So this is our lecture number 9, wherein we discussed about how we can determine the surface tension of solids. So firstly, we discussed how we can determine the surface tension of liquids. Then what are the various methods to determine the contact angle of solids of liquids as well as the finely divided powder. And lastly, in lecture number 9, there is a there are methods describing how we can determine the surface tension of solids. So what are the various methods? We can see here we have listed certain methods. First is surface tension of the melts. So when you melt a solid, then you can determine the surface tension of that melt. So that will give the surface tension of that particular solid. Next is heat of solution. So the difference between the heat of solution of pores and the finely crystalline material will give the particular surface tension of solid. Another is abrasion and grinding. So the mechanical energy which is required to abrade or particularly grind a solid includes the interfacial work along with heat and as work of deformation. So basically what they are trying to say is that when you abrade or grind any particular solid, this corresponds to their particular interfacial tension, or which also includes the work of deformation and heat generated. So next is work of cleavage. So cohesive energy per unit length must overcome during cleavage. What is cleavage? Cleavage is basically breaking off or dividing any kind of solids, cleaving any kind of solids basically. So when you cleave a solid, this work done can be directly proportional to the surface tension of that solid. Next is dependence of solubility on grain size. So in case of solids, the certain grain size is there. So the solubility of this grain size can also help us determining the surface tension of solids. Then we have supercooling of melts. So if you supercool the melts, it also helps in determining the surface tension. Apart from that, we have adhesion force and again wettability and contact angle, which is an indirect method. So adhesion force can be given in the next column. As you can see, force of adhesion is equal to 3 by 2 pi r w, which can be written as minus 3 pi r gamma sv, where r dash is r1 r2 divided by bracket r1 plus r2. So lastly, we can also how we can measure this adhesion forces. There is basically this atomic force microscopy which helps to measure the force of the adhesion force. So adhesion force is determined from the deflection or the jump distance of the cantilever, that is delta ds, when the bond breaks. So K is the finite stiffness. In the next equation, as you can see, it is written F is equal to K delta ds is equal to K multiplied by del. So this del is the finite amount of deformation, that is deflection, and delta ds is when the bond breaks. This is the deflection or the jump distance of the cantilever, whereas K is the finite stiffness. So this is basically an instrument AFM. You might have also heard it. Next we have total internal reflection microscopy, TIRM. So from this, the intensity of the reflected beam or the motion of the particle can be recorded about its mean separation d naught, that is distance in real time, to an accuracy of about 5 nanometers. So these are basically certain instruments which helps in measuring the adhesion force. So that's all was discussed in the last week, that is week 3 lectures, and pertaining to that is lecture number 7, lecture number 8 and lecture number 9. So we'll try to solve questions related to all these lectures. So moving on, the first question, which is, which of the following is not a detachment based method for surface tension measurement? Right now we just discussed what are the various detachment based method. So if you can recall what were the detachment based method, do we need to uh, why we need these kind of methods. So you all have options, that is A, rotating drop method, B is drop weight method, C is ring method, and lastly D, Wilhelmi slide method. So you have to analyze which is not the detachment based method for surface tension measurement. So recall about what was rotating drop method, what was drop weight method, what was ring method, and lastly what is Wilhelmi slide method. So we just discussed a bit of each of these methods. So I'll give you 1 minute if you can just think about it. So three of the options are detachment based method basically, and one is not.
Ma'am, option A, rotating drop method.
Okay, fine. I think you have very well understood most of the concepts. So it is a very easy question. You just need to go through the lectures once, then only you will be able to solve most of the questions. So the correct answer is, of course, we have rotating drop method. So as you can see, various detachment based methods are drop weight method, which is option number B. Next is ring method, option number C, and option number D, Wilhelm slide method. So in case of what do we call as detachment? Detachment is basically any drop detaching from the capillary. We call it as detachment based methods. Whereas rotating drop method is based on its shape. Rotating is rotating the drop, and shape analyzing is there in this case, right? So you are correct. The correct option answer is rotating drop method. Fine. All we'll move on to the next question. So the correction factor F in case of drop weight method is equal to. So as if you recall, what is this correction factor, and in which of the methods we use this correction factor, which in which of the methods this correction factor is being involved. So your options are A 1 by V, B R by V, C R by V to the power minus 3, and lastly R by V to the power 1 by 3.
Option D.
Option number
Option D, ma'am.
D.
Yeah.
Okay, fine. Okay, we'll look at the answers. So we also discussed this question. So yes, you are correct. We have the answer as option number D, that is R by V to the power 1 by 3. So in case of drop weight method, W dash is given as 2 pi R gamma F, wherein F corresponds to R by A, which is directly proportional to R by V to the power 1 by 3. So you can just see from this equation, F is inversely proportional or directly proportional to R by V to the power 1 by 3. Yes, fine. Uh, I hope these questions is like straightforward questions. We'll move on to the next question. Question number 3. So which of the following is also known as stalagmometric method?
Drop weight method.
Okay, drop weight method.
Yes, ma'am.
Fine. We'll see the answer. Uh, I hope Rajat is also able to catch up. Okay, let's discuss the option first. So A is sessile drop method, B is Wilhelm slide method, C is drop weight method, and D is ring method. Okay, so you're quite correct. So drop weight method is also known as stalagmometric method or drop volume method. Okay, fine. So sessile drop is based on shape. Wilhelm slide method both can be used for in case of contact angle as well as in case of surface tension measurement. Drop weight method, it is also known as stalagmometric method or drop volume method. Lastly, we have ring method. So ring method is also known as, if any question arises, what does ring method is also known as, how will you answer that? Or do you have any idea what is ring method also known as? The ring method is also known as do know you ring method. If you will go through the lectures, you will also get to know. It might be written somewhere. It's known as do know you method. Hope you remember it.
Yes, ma'am.
Okay, fine. So next question we have is, which of the following is the instrument used for contact angle measurement?
Contact
First
angle.
is,
Ma'am,
yes,
option
Krish.
B.
Okay, fine. Yes, we already discussed this in our
Yeah.
lectures recap just a few minutes ago. So first option is
Yes.
tensiometer, second is goniometer, C is pycnometer, and D is viscometer. So okay, fine. Goniometer is the correct answer. Option number B. I hope Rajat is able to also catch up. So tensiometer, it is used for determining the surface tension. Goniometer, as I just said, Zisman and co-workers used this instrument first. Like who did it first? Zisman and co-workers. Uh, Third is pycnometer, which is used for measurement of density. And lastly, we have viscometer, which is for viscosity measurement. Fine, very well. We'll move on to the next question. Question number 5. So, which of the following is Young-Laplace equation?
Option A.
Okay, very well. It's the correct answer. So, wherein we use this Young-Laplace equation?
Young
In which method did we describe this? Which method is based on Young-Laplace equation?
Ma'am, 1 minute.
Okay, so pendant drop method is basically used. In that method, we have this Young-Laplace equation. Del P is equal to P internal minus P external, gamma 1 by R1 by plus 1 by R2. Next we have gamma del rho GH square by 2. Option number B. Option number C is gamma is equal to angular velocity to the power square del rho R square by 4. And lastly we have W is equal to 2 pi RF. So you'll also see what are the other options wherein we use these options. So the second equation B, it is for sessile drop method. First option, that is Young-Laplace equation, is used in pendant drop method. Okay. So maybe you might get any question other than this. So they may also give you equations for rotating drop method or drop weight method. So you must also remember these equations as well. Option number C is for rotating drop method and option number D is for drop weight method. Fine. We'll move on to the next question. So the next question is, spinning drop method for surface tension measurement is based on A. Tate's law, B. Young-Laplace equation, C. Young equation, and D. Von-Gutt equation. So lastly, in just before this slide, we talked about the pendant drop method, which was based on Young-Laplace equation. So already you can rule out the option number B, that is Young-Laplace equation. Then rest we have left with A, C, and D. So try to recall what was Tate's law, Young's equation, Von-Gutt equation. I also mentioned about Von-Gutt equation while going through the recap of the course content. So when you recall the spinning drop method is also known as the rotating drop method. So don't get confused between rotating and spinning drop method. Both are the same thing. Okay, we'll discuss the answer to the question? So the correct answer is option number D, that is one gut
Yeah, now I
equation.
get it the
Okay,
answer.
fine. Yes, I just went through the recap. So I mentioned there what is this one gut equation and where you use it,
Yeah.
right? So first option, that is State's law. It is W dash is equal to 2 pi r gamma f. So question, we have the spinning drop method or the rotating drop method for surface tension measurement is based on. So already I told you the B option is for pendant drop method. Question number 5 was based on that. Option number C, Young's equation, that gives the relation between the contact angle and the interfacial tension. So it does not gives any like basis for any of the method for surface tension measurement. Rather than it gives the relationship between the interfacial tension and the contact angle, right? And lastly, the von Gut equation. So gamma is equal to,
Um,
okay, angular velocity square del rho and r to the power
okay.
cube divided by 4. So in this case, the interfacial tension, that is gamma, between any two liquids or medium with the density difference of del rho rotating in a glass tube that I said as capillary, which have the drop radius of r, is perpendicular to the axis of rotation with angular velocity, which can be given by this von Gut equation. So don't forget that von Gut equation is the basis for rotating drop or spinning drop method for surface tension measurement. Fine?
Yes, ma'am.
Okay. Let's move on to the next question, which is question number 7. So the thin plate used in Wilhelm's slide method is made up of, option A is silver, B copper, C platinum and D stainless steel. So when you go through the lectures, I think there is also this thing mentioned very
Ma'am, platinum.
yes, uh, you're correct. The answer is D. Sorry, C. That is platinum. So either it is ring or the plate, which is used in Wilhelm's slide method or the drop method or the ring method. Uh, sorry, not the drop weight method. In the ring method, we have this ring or the slide made up of platinum. Of course, silver, gold, these are also uh, not cost friendly. Platinum, however, platinum is mostly used in case of these plates and rings. So yes, the correct answer to this is platinum. So platinum is used as the material for the ring. Why? Because it is optimally wettable due to its very high surface free energy, and therefore generally it forms a contact angle, that is theta of 0 degree, that is cos theta is equal to 1 with any kind of liquids. So we don't want any extra dependence or interference of the material that is used for these slides and these rings. So we usually, and for anything, we try to use such inert kind of material, right? Which won't also react with the liquid. Fine. Seventh question is, I hope this question is also clear to you. Okay. We'll move on to the eighth question. The eighth question we have is, which of the following is not a method for determination of surface tension of solids? So in the lecture number 9, we discussed about the determination of surface tension of solids. So we have four options. A is heat of solution, B is maximum bubble pressure, C is surface tension of melts, and D is abrasion on grinding. So you have to point out or tell me which is not a method for determination of surface tension of solids. Specifically, it's written solids. And three of these methods are able to determine the surface
Ma'am,
tension of
option B,
solids.
maximum bubble pressure.
Yes, you are correct. The correct answer is option number B, maximum bubble pressure. Yes, so we mentioned various methods. So heat of solution is one of the methods. Again, surface tension of melts can be used for determination of the surface tension of solid as well as abrasion and grinding. Whereas maximum bubble pressure, as I said, this technique is applicable to the study of surface tension of surfactants and polymer adsorption from the solution. So basically this is not a method for determination of surface tension of solids. Fine. I hope till 8th question everything is clear and the questions are very straightforward, and if you have went through the lectures for even for 1 or 2 hours, you might be able to give the answer very easily. Okay, we'll take 1 minute of rest, or say 1 minute of break, and then we'll move on to the numericals part of the session. Fine.
Okay, ma'am.
Okay. I hope Rajat is also able to understand with the pace we are going. Today we are going a bit faster. I think I am more inclined towards solving the numericals because, of course, the theory part is you yourself can understand it, but for the numericals part, uh, I think if you solve with me, then please, I would urge you all to use a calculator and a pen and paper if you have it and solve with me, so you may also remember or recall you everything when you are giving your actual examination or solving any other assignment as well. So some of the questions from the numerical portion are very similar to what the course instructor has also discussed in his lecture. So if you have paid attention to the course to the lecture that has been uploaded in the NPTEL platform, you might be able to even solve these questions. Well, so the ninth question, we may move on and discuss the numericals for the today's session. So ninth question is water rises through 9.11 centimeter in a capillary of diameter 0.64 mm at 30 degrees centigrade. You have to calculate the surface tension in Newton per meter at that temperature. So you have four options. A is 142.99 Newton per meter. B is 156 Newton per meter. C is 1.43 into 10 power minus 1 Newton per meter. And D is 156 multiplied by 10 to the power minus 3 Newton per meter. So I'll give you 1 minute if you can try to solve this question. Okay, can you see while I am inking the slide?
Yes, ma'am.
Oh, okay, we'll discuss. So the correct answer to this question is option number C, which is 1.43 into 10 power minus 1 Newton per meter. So this is based on, if you go back to the slides, one of the formulas or equations, as you can see, is based on this similar. In case of drop weight method, we use certain kind of equations. So this is del P is given as rho GH is equal to 2 gamma by R. Right. So I have given you the equation also. You have everything given in the question as well. If you can still able to calculate it and give me the answer, it's very straightforward. Rho is the density, that is density of the water. G is your gravitational constant. H is the height, that is water rises to 9.11 centimeter in a capillary. The height of the capillary is 9.11 centimeter. And then you have to find the surface tension, that is gamma divided by r. So you have been given the diameter as 0.64 millimeter. So you can take out the radius through this dia, put it in the equation and try to give me the answer for this. So we'll slowly slowly try to solve the question. Just wait a minute. There is certain something happening right now. Just give me a minute. Okay, I'm not been able to access the presentation or even the link. So if you can just rejoin the link if it is possible. There's some problem, there's some issues. Just wait. Okay, I lost my connection. Okay, I'm sorry, there was. So, yes, I think I lost my connection in between. Sonali, can you answer me? Are you able to listen to me now?
Yes, ma'am.
Yes. I lost my connection in between, and right now I'm unable to share the presentation. So I'll try to resolve this issue because just wait a minute.
Okay, ma'am.
Can you see the slide now?
Ma'am.
Okay. So I'm sorry there was certain glitch. We'll try to, and the glitch is till now, but I hope I'll be able to take this session as of now. Okay, fine. So let's move on and try to solve this question. So what was the question? Water rises through 9.11 centimeter in a capillary of diameter 0.64 mm at 30 degrees centigrade, and you have to calculate the surface tension in Newton per meter at that temperature. Okay. Okay, I cannot. Hmm, just wait.
Okay, ma'am. Can you share the next question?
Hmm. Actually, I cannot ink the slide. This has been opened in safe mode, so there is this option for inking uh, is not appearing, and I'm also unable to open my PPT in.
Okay, ma'am. No problem.
Yeah. So wait a minute. Yeah, fine. Now I'll be able to ink it. I don't know. Okay. So let's begin. So what all things are given in the question? We have our rho. So the density of water is around 1 gram per centimeter cube. Fine. Are you able to look into the slides? Is it visible?
Yes, ma'am.
Okay, okay,
Yes, ma'am.
okay.
It's visual.
Okay. So we'll solve it very soon. Very fastly we'll solve it. So next we have this G. We know it as 9.81 meter per second square. And then we also in the question it's given as H as 9.11 centimeter, and we have the diameter as, how much was the diameter? 0.64. So the diameter was 0.64 mm. So radius you can take out from the diameter. So diameter by 2 gives us the radius, that is 0.32 mm. So this is in gram per centimeter. This is in meter per second square. So can we convert this in terms of centimeter? So what it will be? Fine. H is again in centimeter. R is in mm. So we can also convert this in centimeter. Fine. So now we'll try to solve. So we have to find the gamma, and I already gave you the equation how to solve it. That is del P is equal to rho GH is equal to 2 gamma by R. So if you try to solve the gamma, it will be rho GHR divided by 2. So simply if you put the values, that is 981 multiplied by 9.11 multiplied by this divided by 2. Can you tell me uh, by calculating? Okay, I'll wind up quickly because already I lost few minutes. So this will come at around something, it will come 142.99. So as you see, this was in centimeter, and the question in the question you were asked about Newton per meter. So if I solve this and I place all the units, you will get something as gram per second square. So now you to convert it in terms of Newton per meter. So 142.99 around gram per second square. So if you multiply it centimeter by centimeter, so this particular thing is equal to dyne. So 1 dyne is equal to 1 gram centimeter per second square. So what will gamma be written as? Dyne per centimeter. Now you can just simply convert dyne per centimeter into Newton per meter. So in terms of Newton per meter, uh, it will come at around 142.9, sorry, you need to just convert it in terms of Newton per meter. So when you convert it, it's something around 1 dyne per centimeter is equal to, fine. So if you convert, it will come as 1.43 into 10 power minus 1 Newton per meter. So this is the answer. So any issue or any problem you are not able to get it in this question, it is a very straightforward, when I told you the equation, I already told you if you simply put the values, you'll be able to get the answer. So the correct answer was option number C, that is 1.43 into 10 power minus 1 Newton per meter. Is it fine?
Yes, ma'am.
So we will move on to the next question. So the next question we have is question number 10, which is a drop of liquid A with density 1.01 gram per centimeter cube on a surface has a height of 0.22 centimeter. The diameter of the drop is 0.67 centimeter. You have to calculate the contact angle. There are four options. Answer to the solution to the question: A 66.58 degrees, B is 60.18 degrees, C is 110.06, and D is 102.72. So if you think about what were the different methods where you can solve the contact angle, one of the method I mentioned about drop shape analysis, where you were having one is tangent methods and another is height and width method. So just see what are the things given in this question. So So the answer to the question is option number A, and we will solve it using height width method. That is tan theta is equal to h by r. Now imagine when you see at the question, a drop of liquid A, which is having a density 1.01 gram per centimeter cube, is on a surface, right? So when this drop is on a surface, it has a height of around 0.22 centimeter, and the diameter of this drop is 0.67 centimeter. Now you have to calculate the contact angle. So try imagining a drop in just above a surface, and then using this particular figure wherein you think the drop as an imaginary circle, and try to determine the contact angle, as in the h is given, the diameter is also given. You have to determine the contact angle. Okay, we will solve together. This is our question number 10, right? So in this particular question, we have been given with the density of the drop, then we have been also given with the height of the drop, you have to find the contact angle, but also we have been given the diameter, right, which is approximately, so when I imagine this as a drop of liquid over a surface, so what will happen, this will be the eye height and I'll have to determine the contact angle. Fine. So if I draw a line here, this is the edge and this is r theta, not this. This is r theta. So can you, using the formula, that is tan theta is equal to h by r. So now r is our, this is our diameter. If I imagine this as my diameter, so d by 2 will be my r, right? So d by 2. So everything is given in a similar unit, that is centimeters. In this question, we don't need to worry about changing the units. So tan theta can be written as, how much is h? 0.22 and d by 2 is 0.67 by 2. So again, tan theta divided by, how much is 0.67 by 2? It's around, something around 0.335, right? I hope till now it is clear. Simple mathematics basics. Then how much will it come? How much will tan theta come as if you divide it? You can use your calculators and give me the answer. So it will be around 0.656. So theta can be calculated by tan inverse 0.656, right? Any issues, any problem till now? If you are not able to solve it, just you need a calculator, put on the values, we'll get the answer. So can you tell me the answer for this theta? What will be the value? Can you calculate? Am I audible? Right, my connection is there. Sometimes you never know when your connection gets lost. Sonali, am I audible? I think yes, probably I am audible. Okay, fine. We'll move ahead. It's theta is given as tan inverse 0.656. I'll calculate it and I'll write the answer. Just wait. So how much will it come? It will come something as theta is equal to 33.29. So we can write it as 33.3 approximately. So as you remember here, this was the theta. So to calculate the whole of the contact angle, you need to also calculate this. So there is actually you have to, for the actual contact angle will be 2 theta, right? So you have to just multiply this and we get something as right. So this is the answer, and when you go back to the question, you got option number A, that is 66.58 is the most closest one, or say is the correct answer. Fine. Are you able to get it? How you have to calculate the question? Okay. We'll move on to the next question. Just give me 1 minute. We'll move on to the next question. That is, we have it as question number 11. That is, the surface tension of two liquids A and B at a temperature of 25 degrees Celsius were reported to be 72.10 millinewton per meter and 27.5 millinewton per meter respectively. So the spreading coefficient as B by A is given as 40. You have to determine the interfacial tension between the liquids, and also you have to verify the determined data using Giri-Falco and Good equation. So whether it is obeying this equation or not. So your options are A 4.6 millinewton per meter obeys the equation. Option B is 4.6 millinewton per meter does not obey the equation. Option number C is 10.54 millinewton per meter obeys the equation. And lastly we have 10.54 millinewton per meter does not obey the equation. So we'll see. The correct answer is option number B, that is 4.6 millinewton per meter, and it does not obey the equation. So how can you solve this question? You have to analyze the spreading, that is SB by A, how can be given as gamma A minus gamma B minus gamma AB. So this will give you the interfacial tension between the liquids, that is gamma AB. And as you already have the values for SB by A, gamma A and gamma B. Also, it has been given, you have to verify the determined data using Giri-Falco and Good equation. So what is this Giri-Falco and Good equation? Is gamma 1 2 is equal to gamma 1 plus gamma 2 minus 2 phi gamma 1 gamma 2 to the power half. So this phi is a function of the molar volumes of 1 and 2. So it should be in unity if molecular diameters obey a geometric mean law. And also if you take the phase 1 as solid and phase 2 as liquid, it can be rewritten as gamma SL is minus gamma SV plus gamma LV minus 2 phi gamma SV gamma LV to the power half. So this is not minus after gamma SL, it is equal. This sign is actually equal. So we will try to solve this question as well. Let's see what are the values given in the question. This is question number 11. So we have been given with this SB by A, which is 40. Also we have gamma A, which is 72.10 millinewton per meter. Then we have gamma B, which is 27.5 millinewton per meter. You have to determine the interfacial tension between these two liquids. Right? So we'll simply try to put on the values in the equation. That is SB by A can be given as gamma A minus gamma B minus gamma AB. Now if you rearrange this, it can be written as gamma A minus gamma B plus gamma. Just try to put on the values. So gamma B by A is 40, gamma A is 72.10. Then we have gamma B as 27.5 and we have to determine the gamma AB. Right? So we'll rearrange and try to solve this. Then we have right. So if you solve this, I'll give you certain time if you are able to solve it. 40 minus 72.10 plus 27.5 is equal to minus gamma AB. I'll give you 2 minutes before I move ahead. Fine. So the answer would be around minus 4.6. So this will cancel out and you will be left with 4.6 millinewton per meter. Fine. So if you go back to the options, so option number A and option number B are the ones which have 4.6 millinewton per meter as the interfacial tension. Now you have to also verify whether the determined data is correct or not using the Giri-Falco and Good method. So we'll also check whether it obeys the equation or not. So when you go back to the equation, as you can see, so using the Giri-Falco and Good equation, we'll try to see whether this gamma AB is similar value or not. So gamma SL is equal to gamma S plus gamma L minus 2 gamma S gamma L to the power half, right? So basically gamma S is A and gamma L is B. So gamma S is 72.10, 27.5 minus 2. How much will you get? Will come some as right. Can you all verify? You are able to look into the slide, right? So 72.10 plus 27.5 minus 89.056. Basic maths. If you have calculator, you can just solve the question. Fine. So this will come as 10.544 millinewton per meter. So the value which we got was actually 4.6 and the value which we are getting here is 10.544. So basically what happens is these both values are not matching, right? So both of these values are not matching when you take it out using the SB by A equation, spreading coefficient equation, and when you take it out using the Giri-Falco and Good equation, both of the values are very different. It is like 4.6 and 10.544 millinewton per meter. So what you can write is, you can write this as, it basically does not obey the Giri-Falco and Good equation. Fine. So if you trace back, option B was the correct one, that is 4.6 millinewton per meter, and it does not obey the equation. Okay. Any queries till now? If you don't have anything to ask, we may just go through the 12th question, which is on a surface, you have the contact angles of water as well as diiodomethane, that is found to be 102 degree and 56 degree respectively. Now you have to estimate the dispersive and polar components of its surface energy And also you have to estimate the contact angle of ethylene glycol on this surface. So basically there is three components which we have to determine. One is the dispersive component of the surface energy, second is the polar component, and lastly you have the contact angle of ethylene glycol on this surface. So you have been given with four options as well as a table is given where you can already see the values of that surface tension in terms of polar as well as the dispersive components are given for water. Next is ethylene glycol and third is diiodomethane. The surface tension of individual liquids as well as the dispersive and polar components are already given in the table. If you try to recall the equations, then you may be able to solve this question as well. So you have been given with four options basically. Option number A, 0.284 millinewton per meter, that is the dispersive component. Second is 30.87 millinewton per meter, which is the polar component. And lastly, it's the contact angle of ethylene glycol on this surface as 81.64 degrees. Similarly, in option number B, it is given 0.111 millinewton per meter, 46.53 millinewton per meter, and 81.64 degrees. And then you have option number C, that is 30.87 millinewton per meter, 0.284 millinewton per meter, and 82.64 degrees. And lastly, option number D, we have 0.111 millinewton per meter, 46.53 millinewton per meter, and 82.64 degrees. So we'll see how to calculate this question as well. So these are the formulas I am giving to you, which are the basis for solving this question. So as you can see, the correct answer to this question is option number C, that is 30.87 millinewton per meter, 0.284 millinewton per meter, and 82.64 degrees as the contact angle. First, 30.87 is the dispersive component of the surface energy, 0.284 is the polar component. So here you have been given with three particular equation. First equation is for the water component, that is gamma W 1 plus cos theta W is equal to 2 gamma SV dispersive, gamma W dispersive to the power half plus gamma SV polar, gamma W polar to the power half. Next is your diiodomethane, that is gamma DI is equal to 1 plus cos theta DI is equal to 2 gamma SV dispersive and gamma DI dispersive. Now you can see that there is no polar component in the second equation. Why so? Because if you have actually put on the values, so it would have come as gamma SV polar and gamma DI polar. So to the power half. So gamma DI polar, that is the polar component for the diiodomethane, is actually 0, right? You can see from the table that the polar component for diiodomethane is 0. Lastly, we have the third equation, that is gamma LV 1 plus cos theta is equal to 2 gamma SV dispersive gamma LV dispersive to the power half plus gamma SV polar gamma LV polar to the power half. So this particular equation, that is your, it is for ethylene glycol, that is the liquid component is ethylene glycol on this surface. Okay, fine. We'll try to solve this question. Let's see what all we have and what all we need to determine, right? So for water, as given in the question, we have theta is equal to 102 degrees, right? Yes. And similarly for diiodomethane, we have the theta as 56 degrees. So if you see the table, you have been given the compounds, and then you have been given the compounds as water, next we have diiodomethane, and lastly we have ethylene glycol, right? This is the liquid actual component, this is the dispersive, and this is the polar component. So for water it is around 72.10, this is 50.8, then it is 47.99, this one is 19.90, then we have again 50.8, and this is again 18.99. So this is the 0. The polar component for ethylene glycol is sorry, for polar component for diiodomethane is 0, and this one is 52.20, and this is around 29. So you have been given with most of the values. You just need to simply put up the values in the equation. So we'll begin with, let's begin with diiodomethane. So let's see, for diiodomethane, the formula, if we go through the formula, we can put it as 1 plus cos theta, and the theta is here. How much it is? The theta for diiodomethane is at 56 degrees is equal to 2. So the polar component is 0, as you know. We'll go through the dispersive component, that is 50.8 gamma S dispersive to the power half. So I'll write it down once again. So this is gamma LV 1 plus cos theta 1. Let's see, we'll take it as 1. This is L1. This is equal to 2 if I take the solid polar and the liquid's polar component. Liquid's polar component. So the liquid's polar component is 0, right? So this will become 0, and then we have dispersive and gamma S dispersive. So this is half. Fine. So we'll try to solve this. This will come as cos 56 is around this, and this can be written as power half and gamma st power half, right? So if you solve this, you will get 50.8 multiplied by 1.59559 as 79.1972, and this will come at around 9. So gamma s t to the power half is divided by 2 multiplied by 7.127. So can you calculate how much we get the value of the dispersive component of the solid? So this is, I have my calculator in hand as well. So let's see. This will come as 5.55, right? So now you have to just square this. You will get the dispersive component of the solid as 30.87 millinewton per meter. Okay, so we already have our dispersive component. We need to solve the polar component as well. So I have taken the diiodomethane as L1, liquid 1. So don't get confused, this is also L1 and L1, this is S, this is L1. I hope there is no query so that we can move further and solve the additional component. It is the next part of the question, that is the polar component for the surface energy of solid. Let's see. So now we did for diiodomethane. Similarly, you need to solve for water. Like for water, as in if you determine the equation in terms of water and the solid surface. So the equation formed here will be L2 1 plus cos theta 2, is the L2 is equal to 2 gamma L2 polar component and gamma subpolar component per half plus gamma L2 dispersive and gamma S dispersive to the power half, right? So L2 for water, gamma L is 72.10. So 1 plus, how much was the theta for water? It was around cos 102 degrees. Now the polar component you have to write. So for water, the polar component is 52.20, and the surface polar component we don't know, which we need to find, plus 19.90, and this dispersive component we just found out what is the dispersive component, that is 30.87. Sorry. Now you can just solve this. So 72.10, how much will cos 102 degree come as? Let's calculate it and write the value. So this will come approximately minus 0.2079. So you may put on the value and start solving it. This will come in minus. So minus 0.2079, and next we have this term. So this will come at around 7.7.20, and then again you have this unknown component, and if you solve this thing, then it will come something 4.46 and 5.55 again, right? So if you go on solving this, then this will come to be divided by 2 is equal to 7.224. Again, writing this here, plus if you multiply these two, how much will you get? will come as 24.753. Right? Now you just need to solve these terms. I'll solve it. $28.5516 minus 24.753 divided by, to solve this term, will come as 7.224. So if you solve this whole thing, the polar component will come to be around 0.284. So if you trace back, you already have your first dispersive component and the second polar component, that is 0.284, and dispersive is 30.87 millinewton per meter. So both of this you already have. You need to now just determine the contact angle of ethylene glycol in this surface. So we'll discuss the third component of this particular question as well. So to determine the contact angle of ethylene glycol on this surface. So this surface already you have the polar component as well as the dispersive component. You already have it, right? Again, you will use the same equation, but here you already know that your liquid component is ethylene glycol, right? So this will be so gamma L for ethylene glycol was 47.99, and you have to actually determine this theta. So now you already have this polar component for the surface and the dispersive component for the surface. You just need to put on the values, that is 0.284, and this the polar component for ethylene glycol is 29 plus 30.87 was the dispersive component for the solid, and 18.99 is your dispersive component for the liquid ethylene glycol. Right. I'll try to calculate it for you. So if you calculate this, so here also we have this half. So this will come something as 2.86, and if you calculate this component, it will come as 24.21, something around this much. Okay, let's see what's the final answer. So this will be 27.07 and we have here 47.99. Now this will come as 1.128. Now if you solve for the theta, so 1.128 minus 1, it will be around 0.128 and theta will be cos inverse 128, which is actually, how much will it be? Will be 82.64. So it will come as 82.64 degrees. Can you all now just lost my connection? Okay, I'm so sorry, I did not. I'll repeat it once again. So we have this contact angle of ethylene glycol on this surface. So you already have the polar and the dispersive component for it. We need to solve for the interface between ethylene glycol and the solid surface, for which we took out the polar and the dispersive component of the surface energy. So gamma LV is gamma LV1 plus cos theta. This cos theta we need to determine is equal to 2 bracket gamma SP, that is the polar component for the solid. Then we have gamma LP, polar component for the liquid, to the power half, plus gamma SD, that is the polar dispersive component of the solid, and then gamma LD, that is dispersive component of the liquid, to the power half. So we just simply put up the values. For ethylene glycol, the gamma LV is 47.99. So, and the polar component for the solid is here the last terminology we got as 0.284 to the power half. Then we have the polar component for the liquid ethylene glycol 29, 30.87 is the dispersive component for the solid, and 18.99 is again the dispersive component for the liquid surface energy. You just need to solve it. When you solve it, you will get cos theta as 1.128 minus 1 is equal to 0.128. So theta will come as cos inverse 0.128. You simply use your calculator and you can get the answer theta as 82.64 degrees. So I hope this session was fruitful for you all. So I'm glad that we were able to solve these questions instead of certain hurdles, like in the middle of the session I lost my connection, as well as uh, there was some certain issues due to which I could not share my PPT with you, but hopefully we traced back. And I hope if you have any other questions you may also speak up now, otherwise we may just wind up the session. I thank you all for joining this session, and we will certainly meet in the next Tuesday session, where we will discuss the week 4 content, course content, as well as we will solve certain questions again to encourage you all for solving the assignment easily. If you have any other questions, you may then again go to the Swayam portal and in the discussion forum, you can ask the question. So we'll leave the meeting now. You all can leave. Good night for today. Thank you.